All right, so we're going to look at this problem. Now, the book is specifically asking you to use technology, and I think this might give us a hint at some of the scales that happen with exponential models. So I'm going to set up what this looks like, and then we're going to look at different ways of solving this. So first, I'm going to pop over here to the blackboard and just write down what we're kind of looking at. We're looking at when a function that we're going to use as a half-life model. So it's going to be 1/2 over the amount of time divided by the half-life, which in this case is 5,700 we're using. And so some initial amount would be out here. But this amount's going to go away for us because we just want when this returns 16%. And so the other function we're going to look at is when we have 0.16 as a constant. And so what we're going to end up with is we're going to end up with this. And where they intersect is going to be our solution. But if you haven't noticed, this creates very big numbers. This should be very large. In fact, when this is 50%, this should be at 5,700. When it's 25%, it's going to be at 10,400. So this 16% is some number greater than 10,400. That's kind of what we want to keep in mind when we're doing it here. So let me go back here and we're going to switch over to Desmos. And I'm going to put in my two functions. I'm going to put f of x is equal to 1/2 to, whoops, let me get that out of there, get out of there, 1/2 to the power of t divided by 5,700. Why does it, whoops, that's going to be an x. I called it x. I'll change it back to x. X. Come on, x. All right. I'm thinking same time. And so this looks like a line, right? But notice I'm really close. We knew the numbers were big. If I were to scroll out, it does have an exponential curve to it. It's just at very large numbers on the negative side. So what we want to find is, if I scroll in, I want to find when it intersects 0.16. And so 0.16 starts out below. So somewhere out near 10,000, these things cross. And if I scroll all the way back, I'm hoping somewhere around 10,000-ish, we get a cross here. And I think where I'm on that one. Let's zoom in a little bit out here so I can see the red line again. Let's get closer and closer and closer. So the red line is still above the blue line, and I want when they cross over. So we're above 10,000. See how technology isn't the smartest tool on this, I don't think. Now, I know some of the calculators, you can get it to focus on the point of intersection, and Desmos should highlight points of interest for us. And so if I go out here somewhere, I get, oh, wait, there's my point. I think that's my point of interest. And it is near 10,000. So right here, it has highlighted the point of interest for me. And it's around 15,070. All right, 15,070. And so our solution is there at 15,070. There's the intersection point. I had to scroll out big enough that Desmos put it there. And like I said, it was past 10,000 somewhere. 15,070 is not too bad. It's not quite 3 half-lives. And that makes sense if a half-life is 5,700 years to go from 100 to 50% to 25%. 12.5% would be at 3 times 5,700, which is 17,100. And so it's just right before that. So it's making sense of what the function can do. We just have to realize it's on a very large scale. Well, let's use our mathematics and what we've learned mathematically to help us get this. So I'm going to come back here and we're going to let our calculator do the work for us. And so what we're going to do is we're going to learn the rules of exponents that we have developed. So we have the output's going to be 0.16. It's going to equal 1/2 to the t divided by 5700. Now, I would like to remove all of these things from upstairs here. So I could take some logarithm, any logarithm, to remove these things out from. I'm going to use ln. So I'm going to get ln of 0.16 is equal to ln of 1/2 t to the 5700. My rule of exponents says I can multiply this in the front, so I will get ln 0.16 equals t divided by 5700 ln 1/2. Well, I want t on its own, so I'm going to divide both sides by ln 1/2. And that gives me t 5700. Well, t then is 5700 times ln 0.16 divided by ln of 1/2. And my calculator will come to my rescue here. Let me pull that out, turn that on, and so I have 5700 times ln 0.16 divided by ln of 1/2. And I get 15,070. And so mathematically, I think our tools are a little bit easier to use just because of the scale of numbers we have. But what the book was asking for was setting up how we could set these two equations.